ITS Georgia members and guests. Thanks for tuning in. And also happy National Paper Airplane Day. Yes, that exists and it is today. So go make a paper airplane and throw it, fly it across your room. As you can all see, we are still virtual, but next month it's going to look a little different from the past 15 months. It's hard to believe it's been 15 months since we've had an in-person monthly meeting. Our ITS Georgia board is continuing to do a lot of different things and to make this a fantastic 2021. We have a lot of exciting things that are being planned, and to keep yourself informed, go to our website as well as looking on our social media platforms. Your voice is also very important to us. If any of you have any input or would like to get more involved with volunteering your time, please do not hesitate to reach on to our technical side of this program. ITS Georgia is partnering with GDOT, and today is the second of 2 open houses that will highlight the traffic signal and ITS specifications, which have been recently updated. The first open house was back on April 28th, and if you missed it, then go and check out the recording. The second open house is this afternoon at 3 p.m. and provides an overview of the pay items in the ITS specifications for use by ITS designers. The open house will also provide information that ITS contractors will find helpful for the bidding and construction process. The 1 hour will provide ample time for your questions, and attendees are eligible to receive a 1 PDH granted by ITS Georgia. It will be held virtually, and as a reminder, will be recorded for your convenience. So be on the lookout for a blast that will be going out by ITS Georgia within this hour. It looks as if our June meeting, this is exciting news. I don't know why I'm so excited. I guess because that we have been virtual for 15 months. We'll have an in-person component located at City Springs to discuss a day in the life of maintenance contracts. Look forward to seeing you guys there who get to make it. And with kicking off to in-person next month, we just may see a pattern starting with July and August also scheduled to be located at City Springs. Registration is open for our 2021 annual meeting. Ty Alexander with AECOM is leading the efforts in planning a fantastic 2021 annual meeting this year. Please mark off your calendars to make the trip down to Savannah, Georgia on September 19th to the 21st for this program with a theme of On the Road Again. Again, registration is open for this event, so go visit our website for more information. As we head into October, expect to see a joint meeting with Georgia ITE hosted by GDOT, and our November awards banquet is scheduled to be back this year. ITS Georgia is moving forward with planning the Southeastern ITS Summit, which is next November of 2022. This will be a regional conference that includes ITS Florida, ITS South Carolina, ITS Tennessee, and GRITS, bringing together 8 states to showcase innovative ITS projects and products. There was a slogan contest last month, and we should hear who had the winning idea in the next few weeks. So be on the lookout for that. And finally, I want to thank all of you tuning in today to our 5th monthly meeting of 2021 to hear about local university happenings. Prepare yourself to be engaged in hearing about what the researchers at Georgia Tech and Kennesaw State are currently working on to advance the state of the art of intelligent transportation systems. From smart loops to move traffic better to super accurate connected vehicles, let's see what the future holds. But before we begin the technical side of this program, I want to present this month's sponsor, as we cannot keep these monthly meetings and our organization goals going without our sponsors. A big thank you to Charlie Witkowski. We look forward to hearing about you and your company.
Thanks, Winter. I appreciate it. Thank you to ITS Georgia for allowing us to sponsor. I apologize for the phone ringing in the background here. Good timing, I guess. Just real quick, I'm not going to take the whole 5 minutes here, but for those of you who aren't aware, we did recently bring on Jimmy Fontaine as our VP of ITS and Smart Cities. So he is heading that new direction of our company for us. As far as he goes, we have brought in a number of products with him, as far as Bosch cameras, LiDAR system, wrong way detection system, as well as manufacturing our own ITS cabinets, which we are working to get on the GDOT QPL here shortly. So if you have any questions or anything pertaining to our ITS or smart cities, or just want to know more about what we're doing at Transportation Control Systems, feel free to reach out to myself or Jimmy, and we'll be happy to assist you in any way possible.
Wonderful. Thank you again, Charlie, and the Transportation Control Systems team for your sponsorship. So now, again, thank you for tuning in today to hear from our presenters, Dr. Kihei, Dr. Guin, and Dr. Guensler regarding university happenings. I'm surrounded by PhDs, so hopefully I'm going to get some of that intelligence just coming through the laptop to me. But before we pass the torch to those three, let me give a brief introduction to our moderator, Dr. Parth. Parth Bhavsar is an assistant professor in the Department of Civil and Environmental Engineering at Kennesaw State University. His research interests include intelligent transportation system, transportation data analytics, connected and automated vehicle technology, and alternative fuel vehicles. Dr. Parth received his PhD degree in 2013 and his MS degree in 2006 from Clemson University, South Carolina. He also has experience in the private sector in developing transportation engineering and planning solutions, most specifically traffic microsimulation projects. He has published in peer-reviewed journals such as the Transportation Research Part C, which is Emerging Technology Transportation Research, Part D, Transport and the Environment and Transportation Research Record Journal of the Transportation Research Board. Dr. Parth has received funding from various agencies such as National Science Foundation, New Jersey Department of Transportation, New Jersey Department of Community Affairs, and U.S. Department of Transportation. And with that, the floor is yours, Dr. Parth.
Thank you, Winter. Welcome everybody to the monthly chapter meeting. As Winter said, today we'll hear from researchers from Georgia Tech and Kennesaw State University. There will be 10-minute presentation from each of these researchers, and if you have any question during the presentation, please type it into the YouTube comment section, and then we will have a Q&A session after all the presentations are done. So we will start from Dr. Billy Kihei. He's a professor in computer engineering at Kennesaw State University. Dr. Kihei, could you please introduce yourself and start?
Sure thing. Thank you, Parth. Hey, good morning, everyone. Let me know if you can see the title slide with the QR code.
Looks good.
Okay, thank you. All right, so we're going to talk a little bit about high accuracy positioning for connected vehicles. Let's check it out. All right, so GPS, real-time kinematics. If this is your first time hearing these words, this is kind of like back in the day when people were saying, yeah, just, there's an app store, coming out. Well, there's RTK coming out for GPS. There's RTK coming out for GPS. It's going to change everything. It's going to revolutionize everything about what we do with our phones for positioning and accuracy. And what we like to do in my lab at KSU is that we want to study these things for connected vehicles and see how this technology can actually do some really incredible things. So a little bit of background on GPS. We should all know this at this time, that GPS provides time and positioning, all from the satellites whirling above our heads. But now GPS is going to provide a safety of life component when it's tied in with our connected vehicles. So those of you that don't know about the basic safety message, which was standardized by SAE a long time ago, they put GPS right in there. You can see the positional for the latitude, longitude, elevation, and positional accuracy. And GPS is so critical for the performance of our CVDX radios, not just from the positioning point of view, such as am I going to hit the other car or not, or can I have preemption at the right time or not, but also for the actual lower layer where the radios communicate, so they don't talk over each other. So GPS is very, very critical. But for this talk, we're going to talk just about positioning. But we did a little study later last year, just asking, can commodity GPS be used for connected cars? And so what we did was we went out to the Cobb County Safety Village parking lot, And we just did some basic tests where we took some anchor points with a very expensive high accuracy system, and we started driving through those anchor points there. So all those cones, we actually got really, really high precision markings there with about an $8,000 equipment, $10,000 equipment loaned from the City of Marietta Water Department. And then we strapped onto our logging equipment just a basic USB GPS dongle, put it on the roof, and wanted to compare it against an accurate GPS module that is found in an older DSRC radio. Notice we had a clear sky, and we drive the car through the points, and that's what we care about right there. Is that the black box there was where our anchor points were, and so we looked at where our points actually landed, and we can go to a little bit of zoomed in spot here. So all the little light dots here, if you can see those, that's from the accurate GPS, and the dark dots there, that's from the commodity GPS. And what we wanted to make sure was we wanted to make sure that there wasn't any positioning falling out of bounds of this black rectangle here. So that was pretty cool. It's like, wow, okay, maybe commodity GPS isn't so bad after all. But we wanted to go a little bit step further because we started hearing about this technology called GPS RTK, which provides less than 2 centimeter horizontal accuracy. This is mind-blowing, okay? Let's look at the use cases as defined by the 5GAA. They did a wonderful study, put out a great white paper. I highly recommend, if you're into this stuff, to go read it. But you can see in the left column here all the use cases and requirements. So high definition sensor sharing, the positional accuracy is 0.1 meters. It's about 4 inches within 3 sigma. So that's a very high fidelity there. Also vulnerable road user awareness for near potentially dangerous situations, collision risk warnings with VRUs, teleoperated driving. All of these require a high accuracy positioning on them. And if you didn't know, back in 2019, Trimble and Qualcomm, which are major players in this space for connected vehicles, they are providing these high accuracy positioning for all of our connected vehicles, and they're hoping to get into the OEM's supply chain here. And this is kind of how this is the big complicated corporate picture of how RTK works. When you hear RTK, just think that the GPS modem on the vehicle is making a phone call to a base station asking, hey, this is the position I'm in. Does that look right to you? And the fixed base station will talk back over the internet and say, yeah, that looks about right, or no, you're off a little bit. Here's by how much you're off. So at a very high level, this is kind of what you can expect for connected vehicles. You have a fixed base station that you're driving by, that you're driving by, and it's talking over the internet and sending those correctional data to the rover part, which is what we call them rovers when they're actually on the connected vehicle. And you can receive those through any type of communication link as long as it's connected to the internet. So it could be a CB to XRSU that's deployed. It could be a cell base station going over a 5G or 4G LTE, even 4G. This is very low data rates we're talking here. These correctional messages, you're talking about, you can, it's about 2 to 6 kilobits per second, okay, is all you really need. So it's a very, very low bandwidth requirement. All right, and so at KSU, we started to deploy our own RTK network in Cobb County because we want to study these things. We want to know, what can we do with this tech? And here's a little demo here of where I'm just taking a regular phone. This is a Samsung S20, and I'm tracing over the K here. I take down KSU out by my house in the cul-de-sac, and I'm just kind of tracing over it, logging GPS points. And what we want to see here is what it looks like. How accurate can just a phone be? And so you see here, we don't really get any KSU GPS markings here. And I put some sneakers there for from a very scientific experiment here. All right, we then tested out a very good external GPS receiver. Now this thing is really good. It can pick up what are called all these different L bands, L1, L2, L5. And I just take this little monopole here and I'm just tracing over the K again. I go back over the KSU and let's see how well performed. Okay, there we go. Wow, external GPS receiver, getting pretty good here. And by the way, that little unit costs about 220 bucks. That's pretty good for that. Now, let's go ahead and set up a base station. RTK base station. There's my student Mohammed, and he worked with me this semester setting this up on our engineering building. And boom, look at that. That's 14 millimeter horizontal accuracy with just a cell phone and a $220 external GPS receiver. And the base station wasn't that expensive either. So this is what we're talking about. And actually, this data point actually did it with a little deployment outside of my garage. That's how accessible RTK is, and this is why it's a big deal for us in ITS, is that these high accuracy position services are no longer 8,000, 10,000 a pop. These things are coming down to below $500. So you're going to see more ubiquitous RTK high accuracy positioning. In our final studies, we looked at 3 different areas on our campus, and we did the same high accuracy GPS markings with the $8,000, $10,000 equipment. And it's kind of hard to see here, but there's these black dots here on these straightaways. That's our anchor points. And we drive our connected vehicle through those points on the road. And that's where RTK pops up. Now, to make it look a little bit better, we also compared it with some other types of devices here. So over here on the top left, as we go through these slides, you'll see that these are the anchor points we wanted to drive through. This was from an old school DSRC radio from 2012. You can see where the points are lining up. Here is a CV2X radio. And by the way, this is, as we know, all the chipsets are based on the Qualcomm 9150, at least as far as I know right now. I'm sure there's some other reference designs, but the GPS for CV2X is built into the actual chip. It's not an external component. And you can kind of see where it's doing some interpolation here, trying to estimate where the car may be. And then right here in the middle, this is where the RTK system is. And you can kind of see the big difference here is that you are lining up almost exactly in the middle. I'll keep flipping through here. And when you go back and watch this later, you can kind of pause and look at the slides and compare against some of these other commodity devices. So here we are around a curve. Again, RTK is just rocking really well. If you zoom in a little bit, you can see how our CV2X radios are kind of interpolating here. So there has to be some extra post-processing, whereas with RTK, you just get a immediate behavior there and very high accuracy. And then finally went up a hill. And again, we're tracking really nicely, even on an incline, which is pretty cool. So going forward, we want to deploy more base stations. We want to study the expected coverage here in the Metro Atlanta area. We want to study these corrections over a CVX RSU. And then we also want to study these, apply this technology for dynamic work zones, where actually someone takes that monopole out there, marks high accuracy, all the traffic cones, and then the RSUs broadcast those to autonomous vehicles. Anyways, that's my talk. Thank you so much. And I look forward to hearing for some questions.
Thank you, Dr. Kihei. Again, to the viewers, just a reminder that if you have questions, please type it into a YouTube comment section, and we will ask these questions to researchers at the end of the presentation. So next is Dr. Angshuman Guin from Georgia Tech. He's a senior research engineer at Georgia Tech. Dr. Guin, why don't you please?
All right, thank you, Parth. You see my screen, the PowerPoint slides. All right. Okay, so hello, I'm Angshuman Guin, senior research engineer in the School of Civil and Environmental Engineering at Georgia Tech. I do kind of, Parth, me, Billy, we all have kind of very overlapping research areas. And I do research in traffic operations, data analytics, connected vehicles. So I'll jump right into it. So we have several initiatives underway around the state for transit signal priority and vehicle preemption right now. In Gwinnett County, emergency vehicle preemption got a renewed interest with the beginning of the connected vehicle initiative that started along with the development of the connected vehicle master plan in 2018. Right. So as part of the Georgia Tech effort, we were tasked with the evaluation of the impact of vehicle preemption on emergency vehicles and to develop methodologies for minimizing emergency vehicle delays while also keeping the impacts on the remaining traffic at a minimum. So in this presentation, I have to assume that everybody knows what emergency vehicle preemption means. So in a nutshell, when an emergency vehicle comes up to a signal and sees a red, with emergency vehicle preemption, we allow the emergency vehicle to communicate with the signal and get a green signal to go through the intersection. Right? I'll leave it at that. So the challenge of doing preemption the old way with the line of sight detection of vehicles is that by the time an emergency vehicle gets detected and it gets a green, it might be forced to come to a stop at the end of a queue of vehicles that are previously stopped at the signal. And now they have nowhere else to go but through the intersection ahead of the emergency vehicle to make way for the emergency vehicle. So the emergency vehicle is slowed down and still experiences some delay even though it gets a green. Right? To eliminate this delay, we want to start the green early enough so that the vehicles in front of it is cleared. To do this efficiently without overly impacting the vehicles in the cross street, it is necessary to obtain a good dynamic estimate of the optimal time that is just sufficient to clear the queue without holding the green for too long. To understand how much impact there really is, that is holding the greens and such, we went with a simulation approach. We built a software in the loop simulation with exactly the same simulation signal controls that are operating the field. We calibrate and validate the model. We create and test the baseline scenario with the naive preemption, and then we test multiple different scenarios to figure out a strategy that will give the optimal solution. So our VISSIM model covers a 6-mile stretch of PIB, Peachtree Industrial Boulevard, between Holcomb Bridge at the south end and Pleasant Hill on the north end. It also includes some signals, one intersection away from Peachtree Industrial Boulevard, as you can see here. So there are a total of 25 signals in the model. We are modeling the PM peak to begin with. So for calibrating the model, we used volumes to begin with. We obtained historic volumes from multiple sources for this purpose. We obtained counts by processing the on-off signals received by the loops by the signal controllers from the field detectors. This data was obtained from the MaxView database that contains the 10 Hertz data of the signal controller events. This was supplemented by volume counts from the ATS PM system maintained by GDOT. However, we have count loops only on the main line in most cases. So the volume on the main line were calculated from these count loops and were accurate, but especially for the through movement. But the volumes on the side streets came from presence detectors. So we expect them to be underestimates of the real volumes. So we supplemented this with historic turn counts, which were available at some intersections, but not everywhere. So once the calibration with the volume was done, we also calibrated the model with travel times obtained from the Redis data, which are probe vehicle data. So next, we validated this against some GPS data we collected back in 2019 before the pandemic. We had deployed some equipment in 17 of the emergency vehicles from 6 of the fire stations around this corridor. These were deployed over a mix of vehicles, including fire engines, ladder trucks, med units. So these reported GPS data every 2 seconds. So we had a very high fidelity data over a 2-month period. So the VISSIM model here is driven using the VISSIM SCOM interface and some Python scripts, which my student Somdut will be happy to explain at some point. But we'll skip over that for now. We need a separate instance of MAXTIME for each signal in the system. That's how the software in the loop works. And VISSIM and MAXTIME runs concurrently in sync and exchanges detection and signal status at every time step. The calibration process is still a work in progress, but based on our tests so far, the travel time results have matched up fairly well with the latest travel times and the trips extracted from the GPS data. As we divided up the mainline corridor into 3 bidirectional segments, the middle segment N2 and S2 matches up very well. not so much on the edge segments, which we are working on resolving. Again, means I present these results here with the caveat that these are very preliminary results. I will skip the MAXTIME setup slides for the sake of time. If you are interested, just reach out to me. My student Somdut will be happy to give a tutorial on that. Let's go straight to the demo file here and hope this plays smoothly enough. Okay. So here's a short demo of how it works. When on the left, you see the VISSIM interface and the vehicle movement at the intersection. On the right, you have the display of the signal state in MAXTIME. In VISSIM, you can set up the signal state as visualization as well to see the signal state. Right now, we have the green on phase 2 and 6. There's no preemption call. So if we give it a second, we'll soon see a preempt call coming up. I'll let it play out. Or maybe just move it forward. So here, once the preempt call has been placed, and we're moving this here to find this emergency vehicle. The yellow one is the fire truck there. So based on the limits of the DSRC radio, we made the detector about, so it's right now the whole approach to the intersection, but we're going to reduce it to 1,000 feet. As the engine crosses the intersection here, we'll see that this preempt call will go into the exit phase started mode, and then it goes away and the signal goes back through the recovery and resumes normal operation after that. For our model, we did a preemption in VISSIM as well. Okay, this started playing it all over again. Let me see if I can go to the next slide. Yeah, skip through that. So this one is a demo using VISSIM's RBC, the ring barrier controller. And if it cooperates and plays, there we go. So in this one, we can see the call from the detector in this stream and the preemption activity on this right here. I'll move this forward a little bit so we can see the detection come up here. You see a 1 here, and it goes into the preempt. We'll again see the emergency vehicle in here. There we go. That's the yellow vehicle. And in this one as well, we'll see that as the vehicle crosses the intersection, the detection goes away, followed by the preempt signal going away, and we take the green away from phase 2 and 6 and give it back to the other cross street. All right, let me keep going. Sorry. So next, we did, here is a comparison of the trajectories of the emergency vehicle going through the corridor. As expected, you'll see that the vehicle avoided getting stuck at the intersection with the preemption. So on the left, this is the without preemption. On the right, it's with preemption. So we see that the vehicle avoided this red in the case with the preemption. And just a sanity check to see that what we are doing makes sense here. So we did several runs to put some confidence bounds on the travel time savings with slightly varying conditions. We made one vehicle go through the signal by approaching at different times within the cycle. We computed the savings limited to the travel time on the approach to the intersection and within like a 12-minute window around the time that the vehicle crossed the intersection. So it's a box plot of the travel times. We see that the average travel times change very slightly for the non-emergency vehicles here, both for the no preempt and preempt case. Well, there's a very little, almost imperceptible benefit for the non-emergency vehicles added from the added green that they got. The variability is large for the emergency vehicle without preemption because of the variability we introduced by injecting it at different times within the cycle. With preemption, the vehicle, emergency vehicle, is able to get through in a much shorter time and a much reliable travel time because it gets the green every time. And for the cross streets, for the non-emergency vehicles, the variation was similar to the main line, except that means the difference is even more imperceptible. Next steps, we are going to add the preemption or enable it at all the intersections on the entire corridor, complete the baseline, study the different scenarios for making the system dynamic by making the time of start of the preemption responsive to the estimated queue lengths that need to be flushed ahead of the emergency vehicle instead of the static approach we have right now with the fixed detector lengths. All right, I will stop there.
Thank you, Dr. Angshuman. So again, just a reminder, if you have any questions, please put your question in the YouTube comment section. Next is Dr. Randall Guensler from Georgia Tech. He's a professor and a group coordinator at Georgia Tech. Dr. Guensler.
Thank you very much. I'll go ahead and share my screen. I'm in civil and environmental engineering, and I'll give the screen share. There we go. And today I'm going to talk about our ARPA-E project that was ran from 2016 to 2018, along with the network modeling work that we did for that, including some of the transport sim applications. And that includes sidewalk sim, at least the structure was there. And these, both the space-time memory that I'll talk about today, that's the STM up there, and sidewalk sim are going to be applied in the ITS4US project that the Atlanta Regional Commission is running. So I'll give you a little bit of background on the ARPA-E project. The main purpose here is to talk a bit about the space-time memory and deep learning. We talked in December about machine learning applications, and I won't go into the machine learning applications, but that is what this is designed for. I'm not going to talk about the NCST energy and emissions modeling that we're doing. That was one of the primary drivers in the ARPA-E project, being able to predict energy use and emissions on all of these different modes and pathways. We'll talk about transport sim, which is the actual program modules that we use for shortest path routines, and then how these will end up in the ITS4US project. So TransNet-Atlanta, we were one of 5 projects that was selected. The goal of the overall program was to try to better predict energy consumption across different transportation alternatives, and ultimately from Department of Energy's perspective, to try to incentivize people to take alternative routes, alternative departure times, alternative modes, whatever you can do to incentivize them to take, to reduce energy use. And some of those things save time as well. We, as part of our project, we're delivering tailored messages to participants. I'll show you how that works. Our only incentive in our program was to provide information to participants so they could choose an efficient pathway. So we had to estimate energy consumption, time, and cost. So it's the cost of owning and operating your automobile, the cost of your transit fare, the cost of parking, and all of those were included in the model. And when we talk about the Dijkstra algorithms and the use of impedance, those were costs that were all included. All the costs were converted to time, and then assess the energy benefits from providing these incentives. The traditional shortest path routines that you get, like when you get into your car and you ask your app, give me the shortest path to work, and it says, well, it's going to be 30 minutes by this pathway. The problem with a lot of the apps is they're using current speeds reported by travelers, what we call streamlines on the network, and projecting your travel time based on what people are currently experiencing. That gets us to the 30-minute commute dilemma where, 10 minutes into that trip, you look down at your app and it says it's going to take you 30 minutes still. And that's because congestion wasn't explicitly accounted for in the algorithm. So newer shortest path routines are employing trajectories through predicted network conditions, so that on your pathway, in deciding which route you're going to take, if you've got a 40-minute travel route, 15 minutes into your pathway, 20 minutes into your pathway, the app is predicting what congestion you're going to be facing on that route. And congestion could be forming, but could also be dissipating. There's no reason to take a longer circuitous route if congestion is going to dissipate by the time you get there. So the idea is to predict speeds that are changing in the network. And hopefully, in this case, when you ask your app, you get a 45-minute prediction. Now, congestion does follow some predictable onset patterns. I got to thank Guin for this slide. Guin works a lot with the Navigator data. We have a repository. We're getting the 20-second data lane by lane. And you can mine these data data sets to look at how congestion is forming and how congestion is being relieved. And the concept here is, if at 8:10 I see congestion upstream on two freeway links that's starting to flow backwards towards my location, that by, I can know in advance that by 8:30, I've seen this happen over and over and over again. It's recurrent congestion that I can predict that I'm going to be driving at 20 miles an hour on that stretch. And so that brings us to the regional space-time memory that we developed for the ARPA-E project. It's a repository of on-road operating condition data. It's at 5-minute resolution. It doesn't really do any good to go at a more refined level than 5 minutes. Traffic signals and signal timing and all that kind of prevents you from doing anything useful if you go down to the 1 minute level. And we're retaining all of this data link by link. The cool thing about the overall space-time memory is it's structured so we can take data from any source. In other words, with machine learning applications, we really don't care where we get the data. What we care about is how good are those data for predicting future conditions. So obviously we have the navigator data feeds that we're getting for the freeway links. We have some arterials that come in there. We worked with AirSage in one of the projects using cell phone tracking data for speeds. Bluetooth and wireless monitoring data can be integrated. We even can bring in second-by-second data from an instrumented fleet, process that, store it, which we did for the Commute Atlanta project before that, and then bring those speeds in as observational speeds. But also another important thing is you can use modeled data. So we can use outputs from travel demand models, dynamic traffic assignment, microscopic simulation to look at potential conditions that we haven't seen in the data set yet that we believe could occur in the future. And we're tracking all the relevant data fields that we need, speed, volume, fleet composition, and the like. And so the idea is that, at 8:10, I'm seeing these conditions on the roadway, but I'm also seeing what happened in 5-minute slices beforehand, and I'm projecting what those travel times are going to be moving through the system. So now, instead of using the streamlines, I can actually use shortest path algorithms that move in time and space through the space-time memory. We use for this the roadway sim and transit sim modules that we developed. These are just Dijkstra algorithm processes for networks. We were using the 203,000 link travel network for the Atlanta Regional Commission's ABM model. That was a 2015 version. We're at about 150,000 links now. We're getting that all set for the next project. We also brought in all of the MARTA fixed rail routes and bus routes and express bus routes so that we have connectivity between these networks. Roadway sim and the STM, which is projecting congestion over time. We kind of cheated on transit sim. We just assumed that the buses followed their schedule and there was enough padding built in so we didn't have to also try to bring in the congestion with the transit, but it's something that could be done in another iteration. And so for ARPA-E, we use the space-time memory to do predictions of alternative routes, alternative departure times, bus and both park and ride and transit-only options. And you get the STM trajectories that are returned, and we can calculate the time, cost, and energy for each of those. And so, for example, for a commute from Sandy Springs to the Bank of America building, your Route 1 direct drive to work is 26 minutes. Your Route 2 alternative is also 26 minutes. It's a slightly different route when you reach the 75 and 85 to Y there. And then you have a one transfer route on transit only. That's 44 minutes. That's walk to bus, ride on the bus, walk to rail, ride on the rail, walk to work. Here you've decided to walk to the rail, so 70-minute trip. And I took out the express bus option, which sends you out up 85 past Brookhaven to catch an express bus up there because there isn't one that serves that travel. Here's one by Park and Ride, which is 35 minutes. So that's kind of that reasonable compromise between driving directly at 26 minutes and taking your transit only options. So Sidewalk Sim is essentially another shortest path calculator. It really doesn't matter what network you have. It can be a communications network, a pipeline network, a roadway network. And in this case, what we're doing is we're developing the pathway network for sidewalks and pedestrian pathways. So the places you can walk or roll a wheelchair. And we're incorporating sidewalk features with this. So it's not just the sidewalk links, but it's ramps, curb cuts where the driveways come across, the sidewalks, crosswalks, and their relevant attributes, both in terms of design standards and condition data. So, is it traversable by a wheelchair? Is kind of the thing to think about, because we're headed into this ITS for Us project to work with the disability community on shortest path, complete path, shortest path routines to get from your home all the way to your building and inside the building that you need to for a public service. Same procedures, it's the same model, really, it's just different cost functions. So now instead of just travel time on the links, you can bring in cost penalties for ADA design standards that are not met, or sidewalk conditions that are impassable or difficult to pass by a specific ADA mobility mode. We've developed networks for East Point, City of Atlanta. We just finished the Clayton County, Georgia network, and we'll be developing, we've done some for Cobb County. We'll be doing the network for the southern end of Gwinnett County for the ITS for Us project. Once you have your networks, you got to inspect them. We have a couple of different tools we use for that. One is Sidewalk Sentry. It's rolling video where we can record the information about the sidewalk. We've got, here we go, sorry. You're getting vibration, you're getting XY position, and then you're also getting a video archive. And that video archive can be scored by reviewers, where you can identify problems with sidewalk width or presence of obstructions or potholes or cracking, anything that you want to ultimately assign a penalty to. And we use the traditional ADA design standard specifications for that. You can also go out with other apps, and in fact, this is our Sidewalk Scout app, where we use this to inspect the ramps and to inspect the curb cuts to make sure that design elements like cross slope, which are a real problem if you're in a wheelchair, they can send you kind of turning towards the street as you're coming across the network. And then as a demonstration, a grad student did this project in December, which was on research last semester, and actually looked at these individual problems, passing widths that are not appropriate, cross slopes, and assigned time penalties to those. This is the application for the Ansley Mall neighborhood that she did for her project. She assigned time penalties of 5 minutes to 1 minute across all of these different variables. And then just as a demonstration, she coded the network and assigned random penalties to these. We don't have all of these networks inspected. We do have most of Monroe. For the City of Atlanta project, so we can actually use the individual penalties for that. But here she applied no impedances. This is just the impedance for the sidewalk surface roughness, so you're not seeing too much diversion there. But then when you bring in all of the other impedances, you can see some real circuitous routes that you might have to take to get around some of the major defects that can't be traversed by a wheelchair. So just to sum up, we'll be bringing both of these initiatives, the STM for roads and transit, and the sidewalk SIM network, into the ITS for Us project that ARC is running. The study area is up here at the corner of Gwinnett County that crosses over into the Doraville MARTA station. And we're both the STM element here and the sidewalk SIM element. ATL Rides and their app will be used for navigation, working with those contractors. It's a big team with the consultants all organizing and coordinating all of this work, but also bringing in all of the ITS elements into this as well. So with that, I will stop. Thank you.
Thank you, Dr. Guensler. So if you have any questions, this is the time to put in your in a YouTube comments. I will start with the question I have for Dr. Billy Kihei. When can we expect RTK to be ubiquitous, and how much does this cost? Dr. Kihei? I guess. So Billy, Dr. Billy, I think we have some lag here. And that is why I'm glad we will have.
Yeah, great question. So ubiquitous, probably within the next 5 years, you're going to start. Oh, hello.
No. We cannot hear you.
Yeah. Yep.
Okay, we have some technical difficulties, so let's start with, okay, Dr. Kihei will type a response in a chat. Let's see if we have any other question. Oh, sorry, I was in a mute. Hello. Yeah.
Looks like we don't have any questions, so.
Yeah, so presenters, do presenters have any questions for each other?
Well, I had questions for Billy, but he's
Yeah, me
having
too.
technical difficulties.
Okay. So again, I just want to remind, if you need a tutorial about VISSIM and MAXTIME integration, you can talk to Dr. Guin. If you want to know about Dr. Guensler, if you don't want to know about, what is the best path, what is the shortest path, then you can talk to Dr. Guensler. And what is the accurate positioning system, then you can talk to Dr. Kihei. So I believe we are good to go. Winter, why don't you?
Yeah, I can take over. It does look like Billy Kihei, Dr. Billy Kihei did get back to us on the question, when will GPS RTK services be ubiquitous? Within the next 5 years, expect more GPS RTK base stations to be deployed in major cities. Agriculture have been using RTK for years, but having GPS RTK as a service for the public is new.
Mhm.
So, and it sounded like it was pretty cost effective per Billy's information. So that's quite nice to see. As we're wrapping up, you guys, first of all, wait a minute, deployments will be to specifically support connected vehicles. So it does look like there are deployments specifically for CV. So that's good to know also. Sorry for some of the technical difficulties, but that's what we get to deal with when we're virtual. No big deal. It was good that we got to at least hear Billy's presentation as well as everyone else's, and you guys just rocked it. Y'all did awesome. You guys got through it, which is leaving some time for us to kind of close out. And also, if there are any other questions out there, I know I state this, but any other questions, just let us know. We can get to any of these presenters and stuff and try to find the answer for you even after. So I'm still getting Billy. How much does it cost? My units are less than $500, not industrial grade. Need to have at least 10,000 to 20,000 for real GPS RTK base stations. So that's a little expensive for the real GPS RTK base stations, but if it's pretty accurate, that's all up in the air to determine what's best. So with the closing, I just want to go back over a few things. Again, I want to thank Dr. Parth. Thank you so much as our moderator, and Billy and Randall and Angshuman, Dr. Guin. Thank you all for your time today. Again, great presentations, great timing, especially on a virtual situation. Look to hear about more of what you guys are going to be doing as the next steps were wonderful too, to let us know what you've got in mind. And we can't wait to have you back on to hear what else is happening. Also, again, if you still have questions, just reach out to us. Again, I want to give a big shout out to this month's sponsor with Charlie and the Transportation Control Systems team. Thank you for supporting ITS Georgia. Tune in virtually today at 3 p.m. And that email should have went out. I've actually already been receiving some information on it. So I saw it come through my inbox, but you should have gotten the blast for ITS Georgia. But this is for the second open house series, the second of 2 open house series, which will highlight the traffic signal and ITS specifications that's been recently updated. As I mentioned in the opening, again, be on the lookout for the blast as far as registering. This event will be videoed, recorded, so you guys can always hop back in and look at it later if you can't make it at 3 p.m. We hope to see many of you at City Springs again for our first in over 15 months in-person monthly meeting on Wednesday, June 23rd to hear about a day in the life of maintenance contracts. So just look forward to seeing some of you in person. Please feel free to reach out to me or any of the board members if you would like to get more involved in ITS Georgia and one of our committees. We have a lot of exciting things on the go and could use all the help we can get. Also be on the lookout for our ITS Georgia emails, blasts, social media announcements to stay informed, as we may have some social networking type events coming up, and also some service projects our committees talking about right now to maybe even help with the students going back to school in August. So be on the lookout for that. If you have any questions, just contact me or go to the ITS Georgia website. But thank you all again for joining us today, and we look forward to seeing some of you next month and wishing everyone a safe and happy Memorial Day weekend. So everyone stay safe and hope you enjoy it. Thanks, everyone. Bye.
Thank you.